Okay, in this video I'm going to talk about the symmedians and the tangential triangle of an arbitrary triangle. So first we'll define the symmedians. So let's say that we have an arbitrary triangle like this. So ABC. So we consider the median of this triangle. Median is a segment that connects the vertex with the midpoint of the opposite side. So BM is a median. Now we consider the bisector. So bisector is the line that divides the angle into equal halves. So BD is a bisector such that the angle ABD is equal to CBD, and the symmedian is defined as the line that is symmetrical to the median with respect to the bisector. So basically that these two angles are equal. So this point denoted by M prime, and so B M prime is a symmedian. Okay, so this is the definition. So this line BM prime is symmetrical to the median BM with respect to the bisector BD. Okay, so now the theorem that I'm going to prove in this video connects the it connects the symmedians with the tangential triangle. So the tangential triangle is a triangle. So like let's say that we have an arbitrary triangle. So ABC and we consider it circumcircle, and we consider the tangents to this circumcircle at the vertices. So this tangent, and this tangent. So we denote these intersection points of these lines by B prime, A prime, and C prime. And so this large triangle A prime, B prime, C prime is called by definition the tangential triangle of the triangle ABC. So A prime, B prime, C prime is the tangential triangle of the triangle ABC. So, and now the theorem is that, so theorem says that if we connect these points A to A prime, B to so the vertices of the original triangle and the vertices of the tangential triangle, so these are the theorem is that these lines are the symmedians of the original triangle. So A prime, B prime, and C prime are the symmedians of the triangle ABC. So in particular, so BB prime, this line, it's symmetrical to the median BM. So like if we put a median here and the bisector somewhere here, BD. So yeah, like it's too much lines here. So if this is the median and this is the bisector and this is BB prime, so then these two angles would be equal. So BB prime is a symmedian in this triangle. So yeah, so let's prove this, and like obviously it's enough to prove just for one of them. It's enough to prove that BB prime, for example, is a symmedian, and the fact that A prime and CC prime would follow similarly. The proof is similar. So it is enough to prove it is enough to prove for B prime. The proof for the other two are similar. Is similar. So okay, so let's draw another picture. So we have this triangle ABC, median, bisector, and so what we do now is let's consider the symmetry with regard to the bisector, right? So symmetry with regard to the bisector. So symmetry with regard to BD. So under this symmetry, the segment AC would be mapped to some segment so let me try to draw it. So the segment, so this is the segment, let's denote it, let's say A2 prime, no, okay, let's denote it PQ. Okay, so PQ, so under this symmetry, with regard to the line BD, so the segment AC is mapped to the segment QP. So A is mapped to Q and C is mapped to P, right? And D is mapped to itself. D, the point D, because it's on the axis of symmetry, it stays at the same point. So now, under this symmetry, now the point M is mapped to a certain point let's call it M prime. So yeah, like earlier we denoted another point by M prime. It doesn't matter, we will not use it. So M prime is this point. So M prime is the middle. So this is the midpoint of PQ, of the segment PQ, right? So the midpoint of the sector AC, of course, is mapped to the midpoint of the symmetrical segment, right? Midpoint of PQ. And so now this BM prime now is, so BM prime is the symmedian. So BM prime is the symmedian that we need. So yeah, it is the symmedian because one of the points on the median is mapped lies on this line, BM prime. So the whole, so yeah, so let's write this more carefully. So BM, so not only M is the midpoint of M prime, and BM, not only M is mapped to M prime, but also BM. So let's write it here. So BM is mapped to BM prime. Yeah, and so now from this it follows that BM prime is the symmedian. Yeah, so because M is the midpoint, so we have that PM prime is equal to M prime Q. So this is the same as to say that M prime is the midpoint of PQ. So now basically what we need to prove is that this point B prime, so when we draw, now we consider this circumcircle, and we consider this tangents, and this is the point B prime. So we need to prove, we need to prove that B prime belongs to this line BM prime, right? So BM prime belongs to the symmedian. We just established that BM prime is the symmedian, and this is exactly what we need to prove, that BB prime is the, we need to prove that BB prime is the symmedian, which is equivalent to say that B prime belongs to the symmedian. So B prime belongs to this line BM prime. So now because of the symmetry we have, denote the angles. So this is alpha and this is gamma, and then this would be the whole angle B would be beta, but because it's because here is the bisector, so we have beta, half of beta over 2, and here also beta over 2. Okay, so So now we draw a line. So yeah, so now we denoted the angles, and so because of this symmetry, we have that this angle is also alpha. PQC angle is also alpha because because it's symmetrical to the angle BAC. So BAC, this angle alpha, is symmetrical to BQP. So now we draw a line parallel to PQ through the point B prime. So we draw a line like this. Until this intersection. So I will remove the what I wrote because I need this space. So I will write it here. So we need to prove that B prime belongs to BM prime, and I put the question mark here. We don't yet know this. It's like we need to prove it. So okay, so we draw a line still not parallel. Yeah. So let me write this. So we draw a line through B prime parallel to PQ. Okay, so then this angle would be also alpha, right? Because it's because PQ is parallel to so this point. Let me denote it some. So this would be T and this would be S. So so because ST is parallel, so ST is parallel to PQ by construction. So because of this parallelness, we have this angle is also alpha. And this angle would be equal to this angle, which is gamma. So the angle BPQ is gamma because of the symmetry with the angle BCA. So BPQ is symmetrical to the angle BCA, and because of the parallel, it's equal to this angle gamma. Right? So now we have, yeah, so now we need to observe that so now we need to observe that this angle, so this angle is so it's an angle between a tangent and a chord, and so it is equal to the to half of the arc which it subtends. Well, it like maybe the word subtend is not correct here, but like it's equal to half of the arc between like that this chord subtends. Well, yeah, so that's how we need to say it. So and this arc is equal to gamma basically, because the inscribed angle BCA also subtends this arc. So basically this angle is gamma, right? So this angle is gamma, and then this SAB prime is also gamma. And similarly here we have the angle, this angle is equal to alpha, because it's an angle between the chord BC and the tangent. So it again is equal to the to half of the arc BC, and the angle alpha, so BAC, is an inscribed angle that subtends this arc, so therefore it's also alpha. So therefore this angle is alpha, and therefore this angle B prime CT. So this angle is also alpha. Okay, let's continue the proof. So basically we established the qualities of some angles. So in particular we noticed that there are two triangles with two equal angles. So we have the triangle AB prime S. So in this triangle, so we have two angles that are equal to gamma, right? So AS B prime is equal to gamma, and SA B prime is equal to gamma. So therefore this triangle is a isosceles triangle. So the sides must be also equal. So SB prime must be equal to B prime A. Right, so now, and the other triangle is C B prime T. So the point C is here. So CB prime T, so this triangle, it's also isosceles because two angles are equal to alpha, angle T and angle C. So the triangle CB prime T, it's also isosceles. So in particular B prime C is equal to B prime T, right? So now notice that, so let me denote it on the picture. So these two sides are equal and these two sides are equal. But notice that actually all four of them are equal, all four of the segments, because AB prime and CB prime, so B prime A and B prime C, these are tangents to the same circle from the same point. So B prime A, this segment, and B prime C, this segment, are equal to each other as tangents from the same point B prime to the same circle. So all four of these segments are equal. So in particular, so okay, let me denote this on the picture. So now I denote all of them equal. So in particular we have that S B prime is equal to B prime T. So in other words, so S B prime is equal to B prime T. So in other words, B prime is the midpoint of ST, right? So now, because it's a midpoint, so now we recall that we have two parallel lines, so PQ and ST. So PQ, this line, and ST, this line. And so we consider, so because it's two parallel lines, there is a homothety with center B. So B is this point. So there is a homothety with center B. So because we have this ST parallel to PQ, so ST parallel to PQ, therefore there exists a homothety with center B that maps these two segments to each other. So that maps PQ to ST. So basically you can imagine it as a scaling of the plane. With center B we scale the plane, and PQ maps to ST. But basically, like the triangles PBQ and SBT are similar to each other. But not only they're similar, but they're homothetic. So with center B. So with center B, when we scale the triangle PBQ, this triangle, when we scale it, it maps to the triangle SBT. And in particular, the side PQ maps to the side ST. But then, under this homothety, so it maps PQ to ST, but in particular it maps the midpoint. So the midpoint of PQ would be mapped to the midpoint. So the midpoint of PQ would be mapped to the midpoint of ST, right? Because under homothety, like when segment is mapped to another segment, like a midpoint of the first segment must be mapped to the midpoint of the second segment. So, but what is the midpoint of PQ? The midpoint of PQ is the point M prime. We denote it as M prime. So this PQ, and this is M prime here. So this is the point M prime, and the midpoint of ST, we just proved it. So we just proved that, here it is, that B prime is the midpoint of ST. So this is the point B prime. So we get that under this homothety with center B, M prime is mapped to B prime, right? So, but now, so M prime is mapped to B prime, but this immediately implies that these 3 points, B, M prime, and B prime, they lie on the same line. Because under a homothety, so a homothety maps when a homothety maps with center O maps point X to a point X prime, so these 3 points always lie on the same line. So like it, homothety maps a line OX that passes through O, through the center of the homothety, to itself. So therefore the mapped point X prime would always lie on the same line OX. So so from this it follows that because the B is the center of the homothety, homothety with center B, so from this it follows immediately that B prime belongs to the line BM prime. And this is exactly what we needed to prove. So, well, what we said that it was enough to prove. So this is the, I put it with the question mark. So it was enough to prove this, to prove that BB prime is the symmedian, which is what we need to prove. So from this it follows that BB prime is the symmedian of the triangle ABC. And this concludes the proof.